Today I'm going to be talking about controls on sediment export across an active rift, the Corinth rift in central Greece. And this is work which I did in my PhD back in Imperial with Alex, Becky, Sam, Vanzi, Lisa, Rob. There was loads of us. So what the motivation behind this is that basin architecture is fundamentally controlled by locus of sediment input, volume of sediment input, and grain size. Now, in the simplified sediment routing system diagram, we have climate and tectonics occurring in the source region, which is causing erosion. This is then pushed down through the system via sediment flux in sediment routing systems, and then it's deposited in the basin, which is also subject to climate and tectonics. Now, in this talk, I'm not going to talk about locus of sediment input or volume of sediment input, but I'm going to focus on grain size. However, I will highlight, in a minute, just after I tell you why also quantifying grain size can be quite cool, is it helps us reconstruct paleoslopes, it enables tectonic subsidence rates to be estimated, it aids in our improving of our understanding of past climate patterns, and it dictates sediment facies partitioning within subsiding depicenters. So I have a paper which is based on the volumes. Here we compare depositional volumes over the last 130,000 years based on seismic data and compared them to suspended sediment flux estimates using a model called the BQuAT model, which was established by Svitsky and Milliman. But I won't be talking much about that. Let's go on to the grain size. So to what extent does lithology, tectonics, geomorphology determine final grain size distribution at river mouths? And how is this sediment delivered to the basin? So we go to the Gulf of Corinth. I won't talk much about this, as Lisa's already gone through it quite a lot, but it's got a really well-constrained climate history, really well-constrained tectonics. It's a closed basin. We've got amazing seismic data. We've got DEM, 30 meter, 5 meters. The extension rates are some of the highest in the world, with 5 millimeters to 50 millimeters in the west. The late quaternary rates, which Sofia Peșlevanidou compiled, shows that there's actually a bell-shaped curve on the south coast. And also we see today from the cores that the basin is predominantly silts and muds. And we see modern Gilbert deltas fringing much of the south coast and north coast. So the key question I'm going to ask is, what is the actual export for the rivers draining into the Gulf? What is controlling this grain size export? What mode of transport is the sediment in? And what is the sediment budget for the Gulf of Corinth? So first off, how did we actually calculate the sediment export? Well, we targeted high flow channel bars. Here we have Sam Brook modeling one quite nicely here. We then scraped off the top layer to remove any winnowing effects, dug a hole, and sieved what was in the hole. Now this constrains the full weighted grain size distribution, and by digging a hole, you actually time average the sediment. So it's actually encompassing several, it's not just an instant data point. And also we had to sieve, we had to make sure that what we sieved was at least the largest class had to be less than 10% of the total volume sediment sieved. So if you find a 10 kilogram boulder, you have to sieve 100 kilograms. And we sieved 47 rivers, which constitute around about 83% of the rift draining. And it's around about 3.5 tons. We did this in the space of about 10 days at the end of August, so it got very hot. So we had a nice parasol here, Sam demonstrating the parasol. And also I managed to get my supervisors to do most of it whilst they were there by the looks of these photos, but it was good fun. And so what is the actual grain size export for the rivers draining into the Gulf? Well, here we have on the top, we split the Gulf into 3 areas: the south coast, the north coast, and the Gulf of Alkanides. Then on the lower graph, we see the cumulative frequencies of grain size. and we color-coded these blue to red, respective of their catchments. So when we look at 0.5, this is the median grain size or the 50th percentile. And the range isn't that big. But when we look at D84 or the 84th percentile or 0.84, this actually have a bigger range, so it actually shows trends more. And what we actually see is that the export coarsens to the west. So there's colder colors are finer, redder colors are coarser, which is kind of cool. The north coast doesn't exactly show that, and the Gulf of Archimedes doesn't, but that's likely because of the sample size. So we're going to focus on the south coast. But firstly, here's the D50 export map for the Gulf of Corinth, and you can see it ranges from sand to pebbles. And you can see in the east, on the south, we've got very finer sands over here. Then we have pebble grade in the center, and then quite coarse again in the very west. This is exacerbated when we look at the D84, the 84th percentile, and we actually can get up to 64 to 128 millimeter size clasts. So they're really quite coarse, especially here in the very west. And then again, we've got finer in the east. So what actually is controlling this grain size export? And we tried to explore a range of things, but firstly, we wondered about geomorphic parameters. Now, these are just two of the geomorphic parameters that I studied. So in the top, we have catchment area against grain size for both D50 and D84. And what you see is that there is very little correlation. And actually, when we did t-statistical tests on the relationship, we actually find that they do not pass the critical. So they're not showing anything. Now, on the lower graph, we've got maximum catchment relief, because we thought perhaps the higher the catchment is, the coarser the grain size, because more landsliding. And again, we don't see very little correlation. And we did this for a few others and similarly found the same. So we thought, what about lithology? Here I have compiled many different studies worth of literature and maps and grouped them into three broad lithofascies. What we have is the Hellenite basement in blue. This is carbonates and flysch. We have Sinriff Unit 1 in the magenta. This is uplifted Gilbert deltas and conglomerates. And we have in the yellows, Sinriff Unit 2, which are sandstone, fine turbidites, and lacustrine siltstones. And I base them into these groups because if you erode a Gilbert delta, you're going to get clasts which are pebbles and cobbles with a matrix. If you erode a lacustrine siltstone, you're going to get silt. So essentially our idea was with catchments eroding more siltstone, you're going to get a finer export. What I did was I took each catchment and plotted them within a ternary diagram where each apex is 100% of one lithology. I then color-coded them to a cyan magenta plot to make it easier to see and scaled them for their D84. Now, the take-home message from this is what you can see is there seems to be much smaller points in the Sinriff Unit 2 corner and much bigger points in the Hellenite basement and Sinriff Unit 1 area. So this implies to me that lithology might be having some control. But the tectonics of the South Coast are very active. So I want to look at tectonics as well. Here we have the, again, the map of the South Coast, and on the bottom graph, we've got lake quaternion uplift rates against distance. And what you can see is that I've just fitted a simple polynomial to it, and these were rates compiled by Peshlevanadou et al. 2019. And what you see is there's a bell-shaped curve with lower rates in the east, highest rates in the center, and lower rates in the west. Now, when I plot D84 against the lake quaternion uplift rates, what you see is you've got D84 here, lake quaternion uplift rates on the x-axis, and they're quite scattered. There's no real correlation between them. However, if you start to just look at the colors themselves, you see that the yellows do seem to cluster, and they do seem to increase from 0.6 to 1.6. So this, and when you look at the Hellenite basement, they all seem to be higher uplift rates, but they're also quite coarse. So this implies to me that lithology is the dominant control on what we see exported at the mouth, but that tectonics has a secondary influence. Now, going into what is the actual mode of transport the sediment is in when it's exported from the Gulf. Well, what I did was I looked at settling velocity divided by frictional velocity. Now, I'm not going to go into the math of this, but it's quite simple, but it's got grain size and channel geometries plugged into these. So it's based on real data. And in the lab, they discovered that if you get a value greater than 3, it's in bed load. If you get between 0.3 and 3, it's a mixed load, which is bed load and suspended. And then finally, if you get less than 0.3, you're in the suspended regime. Now, when we look at our graph on the right here, we have cumulative frequencies at the top, and we have it D50s in blue, D84 in black, and then a typical sand in orange. And I've highlighted each regime of bed load, mixed load, and suspended. Now, what you can see from this graph is that D84 is predominantly in bed load, and D50 is also in bed load and mixed load. So this shows to me that D84 and D50 are predominantly transported in bed load, which, and then when we take a typical sand-sized particle and we put in the measurements, we actually find that they totally reside in the suspended load regime. So this implies to me that this grain size, coupled with the channels we have in the Gulf of Corinth, means that sand size and smaller than 0.25, just export straight out into the Gulf. It's bypassing the system, which is why we see a lot of muds and silts in the basin. Now, just for later on in the talk, the threshold between mixed load and suspended load, when we did the median for all of the rivers, we actually get a grain size of around about 0.85 centimeters. This will become much clearer later. So what's the actual sediment budget for the Gulf of Corinth? Well, this is from my first paper, but this is the total sediment budget for the Holocene. And we've got sediment discharge for the Holocene on the y-axis, and we've got grain size on the x-axis. And you can see I've thresholded them between 0 to 0.085, because this is the grain size which I believe is the mixed to suspended load transition. Now, what I found from the first paper is that the Holocene basin volume, this is core constrained, is 35 kilometers cubed. Now, to get a bed load, all I did to estimate was I just took a typical threshold ratio of 35 to 65 bed load to suspended load ratio. So I took the 35, applied that ratio, and I got 18 kilometers cubed. I took this ratio because it's based off real data, and I've given error bars based on the possibility of 25 to 75 and 45 to 55. So there's quite big error bars, but it's obviously going to be smaller. However, what is the actual grain size distribution within this bed load sediment budget? So how do we do this? Well, I've shown that D84 is in bed load, so we're going to be calculating the bed load sediment budget. We take each of these cumulative frequency plots for each river, frequency against grain size, and we differentiate them, where the area under this graph is now 1. I then exclude anything less than 0.85, and I only treat the data bigger than that. And what I do is I multiply it by a bed load sediment flux, so I repopulate this curve. So I use the B-quart suspended sediment flux from the first paper. However, I use the 35 to 65 ratio to turn it into a bed load sediment flux, and just to explore what it looks like. And what we see here is the bed load sediment budget. So we've got the bed load sediment discharge for the Holocene, and this is in kilometers cubed, and we've got grain size on the x-axis. And what you see is that the majority is between 1 to 2 centimeters, 2 to 4, and 4 to 8. So this is really coarse bed load sediment budget. Actually, 79% is pebble grade and coarser, and 21% is coarse sand to pebble. So this bed load sediment budget is likely the bed load sediment budget of the Gilbert deltas that we see today. And here we have just a few pictures. So this is one of the uplifted Gilbert deltas. And actually we were there during a storm. And actually during a storm, the bedload isn't mobilized, it's actually just muds and silts exporting in these hypopycnal plumes, which gives an idea why they're much more readily mobilized and they're making up the majority of what we see in the basin. So finally, to conclude, we measured the full weighted grain size distribution and found a coarsening to the west. We found that lithology is the dominant control on final grain size distributions. We hypothesize that this is because rock type strongly influences both initial grain size production in landslides. This is based on a wealth of data, and then subsequent abrasion, which again, there's a lot of data to support this. However, we think that tectonics dictates the regions with the highest erosion rates. We can show that the majority of what we've measured at the river mouth is exported in bedload. So there's finer material in the basin, as Lisa showed. So therefore, there must be significant bypass of sand grain and finer material because we're sieving and we don't see it. So our data here explains the modern fascist partitioning around the Gulf, where we see large Gilbert deltas fringe and the main basin is predominantly mud. And finally, our derived sediment bedload budget, we've shown the derived bedload sediment budget for the entire rift, which shows a high proportion of coarse material, but lacks sand grade or finer, is likely the sediment budget for these Gilbert deltas. So this is all in my paper in Basin Research with the same title. It got published this year if you want to go into any more depth, and there's a ton of supplementary data as well, so you can really critique it if you want to. Any questions? And this is just a picture of us after we finished our first river, and it was very hot.
Thank you, Stephen. I can imagine how terrible that must be to sit in the sun there and thieve 3 tons of rocks.
Yeah.
We don't have a question in the chat. Does anybody have a question right away without typing? Then you can just unmute yourself and ask it. If that's not the case, you actually managed to have your conclusions up at minute 15. So we then,
really?
we then just continue to the next speaker.
Okay, cool.